Okay, so this turned out to be a three-part series actually, just to break this up nicer in the videos. And so what we did in part two of this was we were able to break up the first function here that was violating our character table rule because it had a dimensionality of 2, and we knew from this rule that we needed to break up both of these actually, e prime and e double prime, into components, and that then made us have that then would allow us to have 6 irreducible representations and 6 classes, right? So the number of rows and columns of our character table has to be equal. And so we just have to do, we figured out how to do with epsilon, the characters in here, these complex numbers. There's no real function that transformed like this, but we showed that the function x plus iy transformed as this top vector. That allowed us to back out what this bottom vector would be. We got to do a similar thing for up here. So in this video, we're going to be crossing out e double prime, and we're going to use a different function. And that function is, how are we going to get that function? We're going to get that function by looking at what this original vector transformed as. It actually transformed, we figured out, as xz and yz. We did that in part 1 of this series. So we're going to do something very analogous. Before, our aggregate function, e prime, transformed as x and y, and we use x plus iy. So the logical thing to do here is now not use x plus iy, but xz plus iyz, right? Very analogous thing to what we did up here with xy. Okay, so now we get to figure out how all these functions transform. The identity is not interesting. We're not even going to write it, right? It just takes xz to plus iyz to xz plus iyz. But we have to do the C3. So C3 operation, xz plus iyz. So again, I'm going to rewrite our rotation matrix here. Remember, it's cosine 2 pi over 3, cosine 2 pi over 3, and negative sine 2 pi over 3, and sine 2 pi over 3, all times xy. That's how xy transforms. So once you have that, then we just plug this in. So we know what x is. X goes as cosine 2 pi over 3x minus sine 2 pi over 3 y. So that's fine, but we're also multiplying this by z. Well, how did z transform? Remember, we have it up here. Z didn't do anything with C3. So z just went to z. So we can times all these by z. Now we have to do the iyz portion of this. So we're going to have plus, and remembering that z didn't do anything. So basically we're doing how y transforms times it by iz. Y transforms, I'm going to put I sine 2 pi over 3, right, this component, times xz plus I cosine 2 pi over 3 times yz. I'm doing the matrix multiplication on this. Okay, and at this point, we just have to factor out something here. This is very similar to what we did at the beginning of the previous part 2 video. Sorry, I guess this should be an arrow here because we're doing a transformation. It doesn't equal this. So what happens to this function when we do a C3, okay? And so what that ends up equaling is, remember, it ended up equaling epsilon, which, by the way, if we expand this out, is e to the 2 pi, expand out Euler's formula, right? So Euler's formula tells us that e theta I equals cosine theta plus I sine theta. So we get here, maybe I should just write that out so we have that. There's Euler's formula. I sine theta. So e to the 2 pi over 3I, which equals epsilon, equals cosine 2 pi over 3 plus I sine over 3. And so this actually ends up, you end up being able to factor out an epsilon. Okay, and so this equals actually epsilon times xz plus iyz. So it's an eigenfunction, and you can FOIL this back out to show that, but you know, you're going to get cosine 2 pi over 3 times xz, that's this term. Then you're going to get I sine 2 pi over 3 times iyz. And then that gets you an I squared, and I squared, remember, is equal to -1, because I is the imaginary number, which is square root of -1. So I get you a negative sign here in that term. Then you have I sine 2 pi over 3 times xz, that's this term. And then you have cosine 2 pi over 3 times iyz, that's this term. So your character here is, we can, you know, write a 1-by-1 matrix, right? Where we took the function xz plus iyz and our times it by epsilon, and we got our result. So we take the trace along this matrix. So the character of C3 is just equal to epsilon. So down here, we put an epsilon. Okay. And very similar thing is going to happen with C3 doing twice. But instead of having 2 pi's over 3's, we're going to have 4 pi's over 3's, because we're rotating 240 degrees instead of 120 degrees. And what that ends up doing, and we showed this in the last video, part 2 video, is when you have that, you end up getting the complex conjugate of epsilon being the character. And the reason why is because the complex conjugate of epsilon, which is just making the complex conjugate, remember, just making the I term negative, that ends up being equal if you evaluate these cosines and sines, 1/2 and negative root 3 over 2's, etc. That ends up equaling e to the 4 pi over 3i. Okay, so taking the complex conjugate of e to the 2 pi over 3i equals e to 4 pi over 3 over I, which is exactly what we need when we're doing a 4 pi over 3 rotation instead of a 2 pi over 3 rotation. So this becomes a complex conjugate. Next one is sigma h. Sigma h, we realized in both videos that the sigma h is in the xy plane. So there's our principal rotation axis, our C3. And so if we have an x vector over a y vector, it doesn't do anything. But if we have a z vector, it's going to go to the negative z, right? So in other words, x goes to x, y goes to y, but z goes to negative z. So when we're talking about sigma h now, xz plus iyz is going to go to negative xz, because z went to negative z, x went to x, minus iyz, because z went to negative z and y went to y, which is the negative of what we started with. So our matrix here, our character here, so this, the character was epsilon complex conjugate of epsilon. Here, it's just going to be -1. Okay? And then we go over here and we have an S3. And so before we got the same answer for when we broke it up. If we had, you know, S3 was epsilon and C3 is epsilon. That's because Z didn't do anything. right? Z just stayed to, that's because we didn't have Z in it. X and Y didn't do anything. But now we have Z. So what is going to happen here? We are going to be doing the same thing as a C3, blah, 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 all this, but we're going to get, instead of it transforming, so this is for S3, because sigma H, remember an S3 is equal to a C3 times sigma H, we do a C3, we get this transformation, right? But now we have, so I can write that down. But remember, we're asking how xz plus iyz, what does it go to? It's going to go to that, but the z's aren't going to stay the same now. The z's are going to flip. So we're going to get epsilon times negative xz, because z went to negative z, minus iyz. Well, we can just factor out a negative 1 there, and our character now is going to be a negative epsilon. Why is that? Because we were able to factor that out. It went to itself, it's an eigenfunction. So our character is equal to a negative epsilon. Okay, and then what if we do an S3 5 times, sorry, which is equal to C3 2 times sigma H. Well, if we do C3 2 times, we know we got epsilon complex conjugate. So again, just writing this out again, we're asking how xz plus xyz goes. But now, again, very similarly, instead of having epsilon conjugate times xz, we have minus xz, because z went to negative 1, minus iyz. So we're going to get negative epsilon, the complex conjugate of negative epsilon. That's going to be our character. So we can put that character right here. Now we just use the trick that we did last time in the part 2 of this series, where we use the fact that we solve an equation where 1 plus 1 equals 2. When we broke this character up, the sum of these vectors have to equal what we started with. So some value a plus epsilon has to equal to negative 1. We did the math last time, and we showed that basically epsilon plus complex conjugate was equal to negative 1. So this value becomes epsilon, complex conjugate of epsilon. This becomes epsilon, just like we had before. This becomes something plus negative 1 equals what we started with was negative 2. Of course, negative 1 plus negative 1 equals negative 2. And this is going to be, we're again use this relationship. And so you're going to have the negative of the complex conjugate plus negative epsilon equals 1, right? If we just negative all this, then we get this equals positive 1, excuse me, right? Negative epsilon, complex conjugate, negative epsilon plus negative epsilon equals positive 1. And same thing here, we have a complex conjugate of negative epsilon, so this is going to be negative epsilon. And there it is. We successfully derived the C3h character table. And we can check, the answer here. Indeed, we are correct. You can see, the key was we had to break these up into functions that had complex components. There were no real solutions here. Here they actually show rotation vectors. We use this x and z one to help us out. I think that was a lot easier than trying to envision the rotation vectors can be a little tricky. You can see various quadratics here that we could have used, but would have made the math probably more complicated. Z was nice. Having quadratics with z was nice because we had just 1s and negative 1s. So that was definitely the right choice.